So, hello to everyone who is watching on YouTube. Since no one has joined the session till now, the live session till now, so I'll be starting in, I guess, 2-3 minutes. So maybe a few people can join by then. So I'll be starting the session. I'll start discussing the problems in like 2-3 minutes. So, since no one has joined the session till now, I guess I'll just start right away for the YouTube audience to see. So, first of all, yeah, hello to everyone. Just to reintroduce myself, I'm Lakshya Saggi, the Discrete Maths problem solving TA for the Tuesday sessions. So I believe this is the seventh session for the NPTEL course. So in this session, we'll be discussing problems related to principle of inclusion and exclusion, and yeah, somewhat related to recursion and stuff like that. So yeah, basically the counting concepts covered in this week. So yeah. So I guess I'll just share my screen and maybe we can get started with discussing the problems. So yeah, let me just share my screen then. So yeah, I hope my screen is visible to everyone who's watching on YouTube. So since no one has joined the live session, so I can't check with anyone if it is visible. But yeah, hopefully it should be. So yeah. So I guess I'll get started then. So as I told, so this week's questions are more on like based on counting and principle of inclusion, exclusion, and stuff like that. So yeah. So first of all, like just to remind everyone of the basic concepts which we'll be using in this session. So yeah, some preliminary concepts. There is not much. So I just wanted to remind everyone of this principle of inclusion exclusion. This has been covered in the lecture contents, but just for the sake of reminding everyone, I'll just discuss what it is. So just I'll just give you the high level idea. So what is basically principle of inclusion exclusion? So it says like let's say we just applied for three sets. So suppose there are three sets uh, A, B, and C. A, B, and C. Then so basically what it says is it helps us count the number of elements in let's say the set A union B union C. And what is this equals to? Maybe I should put this in next time. Maybe. So this is equals to. So this is basically that cardinality of A union B union C is nothing but the cardinality of A plus cardinality of B plus cardinality of C minus cardinality of A intersection B. So how do we calculate this? So basically, so suppose we want to count the number of elements in A union B union C. So we count the number of elements in A, then count the number of elements in B, then in C. And by that time, how much elements we have overcounted, we try to subtract them. So we have added the elements which are in A intersection B twice. So we subtract them one time by subtracting this A intersection B term. Similarly, we also would have counted the elements in B intersection C twice. So we'd subtract this B intersection T term, C term also. Similarly, we would have counted this C and A twice also. So we subtract that also. So this is C intersection A. But now while subtracting, we would have subtracted the term A intersection B intersection C thrice. It will be subtracted here, it will be subtracted here, it will be subtracted here. So we sort of added back. So we sort of add back the term A intersection B intersection C. So it's A intersection B and like intersection C. So yeah, so this is principle of inclusion exclusion. So this is nothing too fancy, um, just by basic counting, we obtain this that the number of elements in the set A union B union C will be nothing but number of elements in A plus elements in B plus elements in C minus elements in A intersection B minus elements in B intersection C minus in C intersection A and overall adding back the elements of A intersection B intersection C. So yeah. So this is the basic principle of inclusion exclusion, which we'll be like using in solving the problems. And like note that this can be extended to let's say n sets also. Here we use only three sets A, B, and C. It can be used for like n sets A1 up to AN, where there'll just be like first pairwise intersection subtraction, then intersections taken on three sets at a time. They'll be in addition form. Similarly, intersections taken four at a time, five at a time, and so on. So yeah, I guess it's easy to extend and must have been covered in the lecture also. So yeah. So I guess then we'll just start off by solving the problems, and maybe I should this has some sort of preliminary or something. So yeah, maybe this suffices. Yeah. So the first question says, so basically since this all of the questions are mostly on counting, so yeah. So first question says us that it just asks us to count the number of ways five boys and five girls can sit circularly so that a boy always sits between two girls. So The basic question is we are given 5 boys, we are given 5 girls. We need to make them sit on a circular table. And the only constraint is that a boy should always sit between 2 girls. So between every 2 girls, there must be a boy. So I don't, um, it's not necessary to draw a diagram for this. I guess everyone can see this easily via oral explanation also that basically for existence there are equal number of boys and girls. So for a boy to always sit between every 2 girls, so between every 2 girls, if there is a boy, then what this means is that suppose we have 5 girls, then the girls have sort of 5 spaces between them, right? So if there are 5 girls, girl 1, 2, 3, 4, 5, then there is a space between 1 and 2. There is one space between 2 and 3. There is one space between 3 and 4, 4 and 5, and 5 and 1. So what we essentially need is to have a boy in all of these spaces. So let me just write it down a bit. So suppose the 5 girls are G1 to G5 in that order. So suppose the 5 seated girls are G1 to G5. Uh, then there must be a boy between G1 and G2. So this is sort of easy to see. So there must be a boy between G1 and G2. Similarly, G2 and G3. Similarly, G3 and G4. And similarly, G5 and G2. So because there are only 5 boys, so this is the only possible way in which they can be seated. So we sort of know that there will be 5 girls, and then in the 5 spaces between the girls, there will be one boy each. So we sort of know the high level idea of how the girls and boys will be seated. So now we need to sort of, since boys and girls, each boy and each girl is distinct, we'll sort of need to permute them, right? So to find the number of possible ways to make them sit, so what we can do is basically, since there are 5 girls, they can be seated in. Uh, so for counting, what we'll try to do. Also, someone has joined. So hello, Priya. So I've just started with the session. I've just discussed what the principle of inclusion exclusion is, and I'm just discussing the first question right now. So I just started with the first question. So the question is that we are given 5 boys and 5 girls on a circular table, and we need to find out the number of ways in which boys and girls can be seated so that a boy always sits between 2 girls. And for counting this, first of all, the argument I'm claiming is that since there are equal number of boys and girls, uh, there must be a boy seated between every pair of consecutive girls. That's the only possible way since there are equal number of boys and girls. And between every 2 girls, there must be a boy. So let's say the girls are ordered from G1 to G5. Girls are seated in this order. Then there must be a boy sitting between G1 and G2. There must be a boy between G2 and G3, and up to like similarly between G5 and G1. So now we are sort of counting so we sort of know the high level idea of how boys and girls will be seated. So there will be 5 girls seated on the table, and between each of the gaps between 2 consecutive girls, there will be exactly one boy seated. And now we need to sort of, since boys and girls, each boy and each girl are distinct, we sort of need to permute over this ordering. So I hope it's clear. If it's not clear, you can let me know in chat also, the things I've discussed so far. So yeah. So now we know that since there are 5 girls which are seated on circular table, so they can be seated in 5 minus 1 factorial ways. Because in general, number of permutations for n people is n factorial. But when we are considering the circular permutations, we have to divide by n also. So this must have been covered in the lectures also. And I guess this is pretty straightforward also. Because in circular permutation, like the permutation of a1 up to an is similar to the permutation a2, a3 up to an, and then a1. So yeah, stuff like that. So yeah. So the 5 girls can be seated in 4 factorial ways, right? And now for each such way, now for and for so we have these 5 girls and they can be seated in 4 factorial ways. And now for each such way of seating these girls, we sort of have these 5 spaces between the girls. Let's say the girls are G1 to G5, then we have one space between G1 and G2, we have one space between G2 and G3, and similarly we have one space between G5 and G1. So there are these 5 spaces, and we need to put these 5 boys in one of these spaces each, right? So basically, each space must get one boy, and there are 5 boys. So we sort of have 5 factorial ways for these boys to be placed between these gaps, because we can permute the boys in any order. And from that order, let's say the B2 comes up in that permutation, the boy B2 comes at the first. What that means is that the boy B2 will be placed between G1, G2. And similarly, B3 comes second, then B3 will be placed between G2 and G3, and so on. So basically, for each such way of girls sitting, for each such way of girls seating, uh, there will be 5 factorial ways to place the to place one boy each between every pair of consecutive girls. So there will be 5 factorial ways to place one boy each between every pair of consecutive girls. This is what we sort of need, right? So there are 4 factorial ways to seat the girls, and for each such girl seating, there will be 5 factorial ways to seat the boys. So the total answer will be, so total number of ways will be nothing but a 4 factorial multiplied by 5 factorial, which is nothing but a 24 times 120. And I believe this will come out to 24, 12, 12, 12 are 144. So it will be 2880. So yeah, so this will be our final answer. I'll just underline this also. So yeah, I hope it's clear to everyone. And if it's not clear, you can let me know via chat and I'll try to explain it a bit better or in more detail. So yeah. So otherwise, I'll just assume that this is clear to everyone and I'll move on to the second question. So yeah. So let's go to second question then. Okay, so second question is, so first one was more related to circular permutation and stuff. Second question is somewhat related to the principle of inclusion-exclusion. So second question says that we need to find the number of positive integers n from 1 to 1000 that are divisible by 2, 3, or 5. So we need to find the number of positive integers n between 1 and 1000 which are divisible either by 2 or 3 or 5. So note that to count this sort of thing, that uh, the numbers which are divisible by 2 or 3 or 5 will sort of, if we just count, let's say, numbers divisible by 2 and 3 and 5 and add them up, we would have sort of overcounted something. Like we would have overcounted the numbers which are divisible by 2 and 3, numbers which are divisible by 3 and 5, and so on. So for this, we'll sort of need this kind of principle, the principle of inclusion exclusion here also. So let me just try to define some notation, and maybe using that notation will be easier for us to understand. So yeah. So let's define some notation. So let's say for a number a, this notation n of a means that denotes basically the number of elements, or let's say numbers between 1 and 1000 which are divisible by A. So let's say I have defined some notation. This n of A means, so A can be a variable, A can be 2, 3, 5, anything. So number of elements between 1 and 1000 which are divisible by A, I'll denote it as n of A. Similarly, I'll define something else. Yeah, this n of A comma B, and this n of A comma B can be basically defined as number of elements between 1 and 1000 which are divisible by A as well as B. So basically number of elements which are divisible by A and B. And similarly, I'll define another thing, which will be, yeah, should just, yeah. So n of A comma B comma C, which will be number of elements between 1 and 1000 divisible by A and B and C. So yeah, something like that. Yeah. So this is some notation which I have sort of defined first. And now using this notation, I believe we'll be able to answer easily. So, so basically we needed to find between 1 and 1000 the numbers which are divisible by 2, 3, or 5. Right? So let me just write it down again. Number of elements divisible by 2, 3, or 5. So this will be nothing but so let's say we just see this sort of principle of inclusion exclusion. So let's say the set A is the set of numbers which are divisible by 2. The set B is the set of numbers divisible by 3. Set C is the set of numbers divisible by 5. So we sort of need to find the numbers which are divisible by 2, 3, or 5. So in essence, we need to find the numbers which are divisible by either by 2 or 3 or 5. So it will be nothing but this set A union B union C. I hope it's sort of clear. So to find the number of elements in this set A union B union C, we can just use this principal inclusion exclusion formula, which just says that to find this, we just need to calculate this term. Number of elements in A plus B plus C minus A intersection B, B intersection C, and so on. So the set A was the number of elements divisible by 2. So, so this will be nothing but n of 2. Similarly, B will be n of 3. C would be n of 5. And now I need to subtract this A intersection B term. So this will be nothing but A intersection B will be number of elements between 1 and 1000 which are divisible by A as well as B. So A was 2 and B was 3. So number of elements which are divisible by 2 and 3. This will be nothing but n of 2 comma 3. Similarly, n of 3 comma 5 and n of 5 comma 2. And then this sort of term A intersection B intersection C term will be nothing but n of 2 comma 3 comma 5. So yeah. So I hope it's sort of clear to everyone what I'm trying to do here. So now calculating this term. So now the idea behind this was, so this term directly calculating was not easy because we may have overcounted stuff and things like that. But what we can claim is counting these sets individually is easy. This n of 2 is easy, n of 3 is easy, n of 3, 5, n of 2, 3, everything is easy. And how is it easy? We can easily see. So n of 2 is nothing but the number of elements between 1 and 1000 which are divisible by 2. So between 1 and 1000, how many numbers are divisible by 2? It will be nothing but 1000 by 2, which is 500. So basically we'll need to take the greatest so number of elements which are divisible by A will be nothing but 1000 divided by A, and we take its greatest integer function. The greatest integer which is smaller than the value 1000 divided by A will be the answer for n of A. Similarly, n of 3 will be number of elements between 1 and 1000 which are divisible by 3. So this will be like 1000 divided by 3 is not an integer, but it will be something like 333.3. So the greatest integer function will be 333 only. And similarly, n of 5 will be 1000 by 5, which will be 200. And now we subtract this n of 2 comma 3 term. So n of 2 comma 3 is nothing but number of elements which are divisible by 2 as well as 3. And what we can claim is, I guess this is an oral claim, that the set of elements which are divisible by exactly 2 and 3 is precisely the set of elements which are divisible by 6. Like what I'm trying to claim is if a number is divisible by 2 and 3, then it is divisible by 6. And vice versa also. That if a number is divisible by 6, it is divisible by 2 as well as 3. So I hope this sort of argument is clear to everyone. Why will this be the case? So we just need to find, so for calculating this n of 2 comma 3, we just need to find the number of elements divisible by 6. So it will be something like 1000 divided by 6 and taking its greatest integer function. So 1000 divided by 6 will be equal to 150, 160, I believe 166. This will come out to be 166. And similarly, this n of 3 comma 5 will be number of elements which when divided by 3 as well as 5, the numbers between 1 and 1000 which are divisible by 3 and 5. So essentially the numbers which are divisible by 3 times 5, which is 15. So we need to find the number of elements which are divisible by 15. So yeah, what I'm trying to say is the elements which are divisible by 3 as well as 5 will precisely be the elements which are divisible by 15. So that's why to calculate this, we'll just need to find the number of elements which are divisible by 15. So it will be like 1000 divided by 15 and taking its greatest integer function. So 1000 by 15 will come out to be 200 divided by 3, which will be something like 66, I believe. So yeah. And similarly, this n of 5 comma 2 will be the set of numbers which are divisible by 10, which will be like 1000 divided by 10, which will be nothing but 100. And then we add this n of 2 comma 3 comma 5. So number of elements which are divisible by 2 as well as 3 as well as 5. So for this, we can just take the product of these numbers 2, 3, and 5. So it will be something like 2 times 3 times 5, which will be 30. So we basically need to find the number of elements which are divisible by 30. So I hope it's clear to everyone. So for this, we just need to find the number of elements which are divisible by 30. So 1000 divided by 30 will give me 1000 divided by 30 will be 100 by 3. So it will be something like 33. So this will be my final answer. So maybe I don't want to calculate all of this. I'll just copy paste whatever value comes out. 734. So yeah, so 734 is the correct answer. Although this can be calculated also orally, but I just thought maybe it's better to just Google it. So yeah. So 734. So basically the number of elements which are divisible by 2, 3, or 5 is equals to this 734. So I hope what I discussed is straightforward and easy to follow. If there is any doubt, then as usual, you can let me know via chat and I'll try to answer it. So yeah. So, so this is the correct answer. So I have underlined this and I guess we can move on to the next question. Right? Okay, so I guess I want to start the answer from here. Yeah. Okay. So the third question says that it is given that a set A has m elements, where m is a number which is greater than equal to 2, and the set B has 2 elements. So now consider the two statements and select the correct option from below. So basically we are given two sets, a set A which has like greater than equal to 2 elements, and a set B which has exactly 2 elements. And now that we need to answer which of the two statements are correct or stuff like that. So statement 1 says that the number of 1 functions from set A to B is something like this, cm comma 2. So I believe this sort of notation of cm comma 2 must have been covered in the lectures also. This just means m choose 2. So cm comma 2 means m choose 2. So basically what this option is saying is that number of 1 functions from A to B is m choose 2 divided by 2. So this is statement 1. And statement 2 says the number of onto functions from A to B is, okay, I guess this should be, yeah. The number of onto functions from A to B is 2 raised to the power m minus 2. So we need to see, we need to answer which of the following statements is correct. So only statement 1 is correct, only 2 is correct, both are correct, neither of them are correct. Any guesses, guys? What do you think? Is the first statement correct? The number of one functions from A to B is m choose 2 divided by 2. So would anyone like to answer in chat or like guess in chat whether this is correct or not? Okay, so maybe I should see this. So let's just look at these statements individually. Maybe I should start in second line. Yeah. So let's just look at statement 1. It says that the number of one functions from A to B is m choose 2 by 2. So this statement is sort of incorrect. And why is this the case? You can sort of directly see also that so there are m elements given to us where m is greater than equal to 2, and set B has only 2 elements. And if you remember discussions from like last to last week, we we told that we discussed that uh, if there is a one function from set A to set B, then cardinality of set B must be greater than equal to cardinality of set A. So I'm not typing all of this. I'm just discussing what we discussed uh, in the past also. So basically, for a one function to exist from A to B, the cardinality of B should be greater than equal to cardinality of A. So I hope this sort of statement is clear what I'm trying to say. And you can easily see why is this the case also, because for one functions, like every element of B should be matched by exactly one element of A only. Like any element of B should be matched by at most one element of. So number of elements in set B should be greater than equal to number of elements in set A. But we know that B only has 2 elements and A has greater than equal to 2 elements. So let's just say, since we want to find out whether this statement is correct for all m or not, so let's just say even if m was only equal to 3, in that case also A has 3 elements, but B only has 2 elements. So B has lesser elements than A, so there cannot exist any one function from A to B. So the answer should be 0 in that case. But here the statement 1 is saying that it should be something like m choose 2 divided by 2. So which is incorrect. So that's why this statement is incorrect. So basically, for any m greater than equal to 2, as size of set A will be greater than size of set B, there cannot exist any one function from A to B. So I hope this is clear to everyone. So now let's check whether statement 2 is correct. So, statement 2 says that the number of onto functions from A to B is 2 raised to the power m minus 2. Okay. So, hmm, so now what I'm trying to, so first of all, let's just see whether this sort of reasoning can be applied here also. So for onto functions, we know if a function from set A to set B is onto, then cardinality of set A should be greater than equal to cardinality of set B. So which is indeed the case here because cardinality of set B is only 2, but A has greater than equal to 2 elements. So this sort of condition is satisfied. So at least the type of reasoning which we applied in statement 1 cannot be applied here. So we'll actually need to count the number of onto functions from A to B. So let's just see what kind of functions can be present from like the set A to B. So what I'm trying to claim here is this can also be calculated using the principle of inclusion-exclusion. So, and how do we do this? I believe this sort of questions should have also have been covered in the lectures. I'm not totally sure, but I'll just give you a high level idea of how to do this, or not just high level, but yeah, I'll count it for you guys. So, to count in general for counting number of onto functions from a set A to set B, we use this principle of inclusion-exclusion. So why is this the case? So to count the number of functions from like, let's say set A to set B, what we can sort of do is we sort of need to find the functions. So what is ontoness? So in ontoness, every element of set B should be mapped by at least one element of set A. I hope you guys remember the definition of an onto function. So I'll just repeat it again. I'll not type it out. That a function from A to B is an onto function if every element of B is mapped by some element of set A. Only then is it an onto function from set A to set B. So to count the number of onto functions from set A to set B, what we can do is basically take the set A. Maybe let's just count the total number of possible functions from set A to set B. Like, let's just say what are the total possible functions from set A to set B, and then we'll try to subtract the functions which are not onto. So to find the number of onto functions, what we can sort of do is take the total number of functions and then subtract the number of functions which are not onto. So instead of directly finding the number of onto functions, we just find out the number of not onto functions and subtract them from total number of functions. So what will be the total number of functions from set A to set B? Would anyone like to answer in chat? I'm asking like what will be total number of possible functions from set A to set B? Okay, maybe I should answer this myself. So let's just say, so total number of function from A to B is equals to what I'm claiming is 2 raised to the power m. And why is this the case? Why is this 2 raised to the power m? So what I'm claiming is so since the function is a function, so what a function is essentially a function from A to B is essentially a mapping in which every element of A should be mapped to some element of B, right? We are just finding total number of functions. So every element of A should be mapped to some element of B. So since there are m elements of A, and every element has basically two choices to be mapped since B has exactly two elements. So since B has exactly two elements, So every element of A has exactly two choices to be mapped. So there are m elements and each of the elements has two choices to be mapped. So the total number of functions with total number of mappings available will be 2 raised to the power m, because m elements, each of those has two elements, two choices. So the answer will be 2 times 2 times 2 times 2. So yeah, 2 raised to the power m. And why is this the case? As there are m elements in A and each element has two choices to be mapped. Right. So this is the total number of functions. So out of these total number of functions, how many functions will not be onto? So, so what I'm claiming is, so what I tried to explain in the starting was to find the number of onto functions from A to B. We sort of find the total functions and then subtract the number of non-onto functions. Right. So here the total number of functions I found out is 2 raised to the power m. And out of these total 2 raised to the power m functions, how many functions will not be onto? So what I'm claiming is there are only two functions out of these which will not be onto. Because for ontoness, basically what we need is set B. So both the elements of set B should be mapped by some element of set A. Only then is it an onto function. But let's say there was this function. So in this total number of 2 raised to the power m functions, there was one function which maps every element to only the first element of set B. Right? So there are these 2 raised to the power m possible functions because each element has two choices to be mapped. Let's say the two elements of B are, let's say, element 1 and element 2. So every element of A will be mapped to either 1 or 2. So what I'm trying to claim is, I believe this claim is straightforward, that a function will not be, one function which will not be onto will be the function where all elements of A are mapped to exactly element 1. Similarly, second function which will not be onto will be the function where all elements of A are mapped to exactly element 2. Because in that case, element 1 will not be covered by any element of A. And what I'm saying is only these two are precisely the two functions which will not be onto. And rest of the functions will be onto. Because in the rest of the functions, both element 1 and element 2 will be mapped by at least one element of set A. So I'll just write it down also. So out of the 2 raised to power m functions, there are exactly two functions which are not onto. One function which maps every element of A to first element of B. Second function is the one which maps every element of A to second element of B. Rest of the functions will be onto. So, so there are exactly two functions which are not onto, and this is sort of the reasoning for that. So what this means is that total number of functions which are onto, so total number of onto function is equals to total number of functions minus number of, let's just say this, that number of onto functions will be total number of functions minus number of non-onto functions. So non-onto function is a function which is not onto. So I guess, so this will be equal to, so the first value is total number of functions is 2 raised to the power m, which we calculated. And from this, we subtract the number of non-onto functions. And what will be the number of non-onto functions? There are exactly two functions which are not onto. So 2 raised to the power m minus 2. So this will be my answer for number of onto functions. And this is precisely what statement 2 is saying. The 2 raised to the power m minus 2 claim. So statement 2 actually is correct. Yeah. Hence, statement 2 is correct. So statement 1 was incorrect, but statement 2 was correct. So what's the option? So option B says that only 2 is correct. So option B is actually the correct answer. Hence, option B is correct. Just handling this. That. Yeah. So I hope it's clear to everyone how we arrived at this. So, so this was the third question. So so if there are any doubts, you can let me know. Otherwise, I'll just move on to the next question. Okay. So let's move on to the fourth question then. And before that, I'll just go in a minute. I'll just go for 1 minute and get some water. So yeah, we'll discuss fourth question in a minute. Hi. So sorry for that. So let's just get started again. So we were now discussing the fourth question. So fourth question is saying basically that we need to find the total number of derangements of 1, 2, 3, 4, 5. So first of all, uh, maybe I should cover the definition of derangements also. This must have also been covered in the lectures, but just to reiterate and remind everyone what a derangement is. So derangement of a set of numbers is basically a permutation of that number, a permutation of those numbers in which ith number does not go to ith place. So let's just say we are given this set of numbers 1, 2, 3, 4, 5. So any permutation in which 1 does not go to first place, 2 does not go to second place, 3 does not go to third place, 4 does not go to fourth place, 5 does not go to 5 does not go to fifth place, will be called derangement. So yeah, so maybe I'll just write this down also. So yeah, what's derangement? So a permutation of n numbers from, let's say, 1 to n, in which ith number does not go to uh, ith place for all I. So this must hold true for all I. So basically not for a single I, like a permutation in which one does not go to second place, but two and three go to second and third place respectively, will not be a derangement. So for a derangement, for every number, one should not go to first place, as well as two should not go to second place, as well as three should not go to third place, and so on. For all I. So yeah. So this should be true for all I. So let's say, if there are only three numbers, 1, 2, and 3, then this permutation 1, 3, 2 is not a derangement. 1, 3, 2 is not a derangement because 1 still goes to first place. Even though 2 and 3 don't go to second and third places, since 1 is still going to the first place, it will not be a derangement. What will be a derangement will be, let's say, 3, 1, 2. So maybe I guess I have discussed this definition, so it should be clear to everyone. So yeah. So now basically in this fourth question, we need to find the total number of derangements of the set 1, 2, 3, 4, 5. So I believe this must have been, like, this is a very straightforward question and must have been covered in the lectures also. So for a set of numbers from 1 to n, so it's proof like how to calculate the number of derangements must have been covered in the lectures that we do this using the principle of inclusion-exclusion. Like we count the total number of possible permutations, subtract the permutation in which one does not go to first place, then subtract two does not go to second place, and so on. So, but the final answer, let's say, I believe in the lectures it must have been derived as. So the formula for the nth dearrangement is nothing but n factorial minus n choose 1 times n minus 1 factorial plus, maybe I should copy this and sort of, yeah, n choose 2 times n minus 2 factorials minus n. So basically this is something like a plus minus alternating series of like this n factorial, which will be total number of permutations. This n choose 1 is basically choosing one of the elements which does not go to its correct place and permuting rest of the elements. And then exactly two of the elements go to correct place and then permuting the remaining elements and then so on. So this is something like a principle of inclusion-exclusion only, since there are alternating signs in principle of inclusion-exclusion also, we have alternating signs here. So this will be something like a dot dot dot. This will continue like this, plus minus and stuff. And the last term will be nothing but so this will continue till, so we can see its rth term is nothing but uh maybe I should just we have to, I'll just write it down. In choosing, then 0 factorial. So this is a formula for. Okay, so Priya is saying that we should explain this. I should explain this formula in more detail. Uh, I just wanted to confirm, maybe I'm not sure. Has this not been covered in the lectures, Priya? This formula for derangements or like deriving this formula. If not, then I can discuss how to get this formula. Otherwise, like if it has been discussed, then I would feel that it's sort of repeating the same thing. So it would be okay. Okay. So you did not listen to all the lectures, so you're not sure. So I will not exactly try, but I can give a high level intuition of how does this formula come into place. Okay, maybe that should work for everyone, right? So basically, this is the formula which we get for dn. Let's just put this formula aside and let's just see how we can derive this formula in the first place. So let's just say maybe I should copy the definition for derangement. So derangement is a permutation of n numbers from 1 to n in which ith number does not go to ith place. And this should be true for all I. Like first element should not go to first place, second element should not go to second place, third element should not go to third place, and so on. So basically, let's just define the sets. Let's say define that Si as the set of permutations where ith number does not go to ith place. So let's just say there are these numbers from 1 to n. So I'm deriving the formula for general n. So there will be like the set S1 will be the set of permutations where number 1 does not go to first place. Set S2 will be the set of permutations where the number 2 does not go to second place. And similarly, Sn will be the set of permutations where the number n does not go to nth place. And basically, for a derangement is a permutation where ith number does not go to ith place, and this should be true for all possible I. So what I'll now claim is set of derangements is equal to S1. So this set S1 intersected uh, intersection with set S2 intersected with the set S3 and so on intersection with set Sn. So note that derangement was a permutation in which ith number does not go to ith place for all I. And I defined a set Si as the set of permutations where exactly ith number does not go to ith place. So for just, let's say for I equal to 1, it just defines the set of numbers where first does not go to first place. Similarly, S2 defines the permutations where 2 does not go to second place. But for a derangement, since it should be true for all I, so to find the set of derangements, we'll just need to take the intersection of all these sets. So is this clear to you, Priya? Why will the set of derangements be equal to intersection of all these SIs? Okay, it's clear. Nice. So basically, what we need is to find the. Uh, so basically, we need to find the size of this set, right? We need to find the set number of possible derangements. So we just need to find the size of this set, the set of derangements. So, and this set is just equal to this S1 intersection S2 intersection S3 up to intersection Sn. So we just need to find out the size of the intersection of this set. And what I'm trying to claim is this can be, so now to find the size of this set, uh, we can use sort of principle of inclusion-exclusion. So note that maybe I'll just go back to the first place. So I defined this principle of inclusion-exclusion for 3 sets, and I told that this can be extended to n sets also. And I defined it in terms of union, that the size of A union B union C will be equal to size of A plus size of B plus size of C minus this, minus this, minus this, and then plus A intersection B intersection C in the end. Right. But a similar principle of inclusion exclusion can be written for like, let's say the set A intersection B intersection C also. Uh, how should I maybe explain this? So, mm, uh, what I'm trying to claim here is that, okay, maybe let's just not do this that way. Maybe I'll just try to explain it here directly. So let's just say I want to find out this set, like this set of like S1 intersection S2 intersection S3 and up to, let's say, the set intersection Sn. So how am I going to do this? So this is how am I going to calculate this? So to calculate this, what I'm trying to claim here is that maybe we know that A intersection B, like to find the size of set, let's say A intersection B, maybe I can do something like add up all of these sets. So you can verify that this will indeed also correspond. This is also a part of principle of inclusion exclusion. So up to maybe let's say Sn. So to find out, okay. So to find out the size of, let's say, sets S1 intersection S2 up to intersection up to Sn, we can just sum all of these, like sum of the sizes of these, but we must have counted a lot of things. We must have overcounted a lot of things, right? While doing this. So for this, after adding all of these S1 size of S1 plus size of S2 up to size of Sn, we can subtract the sizes taken two at a time. S1 union S2, like basically similarly S2 union S3, and similarly like taking everything two at a time, and then we'll add everything union taken three at a time. So we'll just add everything taken three at a time, and then we'll subtract everything four at a time. We'll add everything five at a time, and so on. We'll continue till we'll obtain union taken n at a time. S1 union S2 till union Sn. And this will be something like -1 raised to the power n. And why will this sort of formula be there? Maybe we can just get a high level intuition for this. This is also nothing but principle of inclusion exclusion and nothing else. Like here you see that uh, we have this formula, right? That A union B union C, size of A union B union C is nothing but size of A plus size of B plus size of C minus size of A intersection B, B intersection C, C intersection C, and A, B, C. So you can just take sort of uh, like you can replace all the unions by intersections and all the intersections by unions. And that point also, this formula should hold by the similar reasonings as we have here. So keeping the reasoning same and just instead of these unions taking intersections, maybe I'll just write down the update formula for that also. So this is also correct in principle of inclusion exclusion. This is not something like a formula, but a very basic thing to observe that size of A intersection B intersection C can also be written as something like this. Okay. So, okay, so Priya is saying it's understood. So I guess it's nice if you have understood this. So maybe you can check something like maybe uh, in this I've done a bit of mistake. Maybe like all of these should be negative and Okay, no, I guess this is correct. Yeah. A union B union C, and then we subtract all of these. And then we sort of add back everything. Yeah. A union B union C I have done. And this will be subtracted here. This will also be. So yeah, something like this is also correct in inclusion exclusion. So now what I'm trying to say is that, okay, so we were here. So when we have this sort of formula, so now since we just need to calculate this thing for calculating the number of derangements, we just need to calculate this term. And what I'm trying to claim is calculating the size of this set S1 is easy because this set S1 is just the set of permutations where first number does not go to first place. So where does the first number, um, maybe I'll come back in 1 minute. I guess someone is at the door. Sorry for that, guys. So yeah. So now set S1 is the set of permutations where first number does not go to first place. So if first number does not go to first place, then we need to find the number of possible ways to count, right? So what I'm trying to claim is using this sort of principle, we can derive this DN formula. Because the number of permutations where first number does not go to first place can be easily calculated, I guess, because the first number has now only n minus 1 choices to go. Now, second number will also have only n minus 1 choices. So it will be something like n minus 1 times n minus 1 factorial or something like that. So you guys can work out the details later, but this is the sort of manner in which we can calculate the number of derangements. This must have been covered in the lectures also. So maybe I'll just remove all of this and we'll just focus on this formula. This is the higher level intuition of how do we obtain this formula? You can work out these details, but for now I'll just remove these. So we know that nth derangement can be written as something like this. So we just need to find out, like, for this, here the numbers are from 1 to 5. So n is equals to 5 here. So we just plug in 5 here. So d of 5 is. So note that even though you should always have in mind how do we derive something, but in general, like, even after deriving, after you understand how do we derive the derangements formula, maybe you can remember this formula directly. Or maybe I can tell you guys how do I actually remember it. Or I don't remember it, I just always derive it. So how do I do another high level idea? So to find out the total number of derangement where no number goes to its own place. So first of all, I take all the permutations. There will be n factorial permutations. And then I choose one number which does not go to its place. And so basically what I try to do is I try to subtract all the numbers. Like maybe so I have this n factorial as total number of ways, and I'll try to subtract the two numbers which go in. So I'll try to subtract the number of permutations in which at least one number goes to its exact place. So derangements is basically the number of permutations in which no number goes to no ith number goes to its ith place, right? So what I'll try to do is I'll try to, from all the possible permutations, I'll try to subtract the permutation in which at least one number goes to its place, like to ith number goes to its ith place. So for that, what I do is, so I'll subtract. So there are I numbers. So there will be n choose one choices. So suppose exactly one number goes to its correct place. So at least one number, let's say, goes to its correct place. then what that means is that there are n choose one ways to select the number which goes to its correct place. Uh, and then the remaining n minus 1 numbers can be permuted in any way. So n minus 1 factorial. But while subtracting this number, I might have subtracted those cases also, where those cases I would have subtracted twice. Like let's say the number 1 goes to first place, number 2 goes to second place. So that sort of case I would have subtracted twice. So I need to add back the cases where two numbers go to their correct place. So that's why I add back, I select two numbers and choose two ways, and then permute the remaining n minus 2 numbers in n minus 2 factorial ways. Now, while adding these back, I would have sort of added something extra, which is the numbers which were taken 3 at a time. So I will again subtract and choose 3 and permute n minus 3 factorial ways. And this will continue till n. So this is the high level idea of derangements, as well as this is the high level idea of principle of inclusion exclusion also. There also we sort of include something, exclude something which we overcounted, include something which we undercounted, and so on. And this is how we derive this formula also. So this n factorial is total number of ways. Then we subtract the number of ways in which at least one person goes to its ith place. Like at least what there exists one I where ith person goes to ith place. Then we subtract where two-person go to exact their places. Then we, yeah, something like this. So now to find out this d5, we can just calculate this 5 factorial minus. So we just put this n equals to 5 here. So it will be. So I hope the intuition for derangements is clear. So if it is not, you can let me know in chat. Okay, it's clear. Nice. So just finding out this value then. So it will be nothing but just putting n equal to 5 here. So it will be 5 factorial minus 5 choose 1, 4 factorial plus 5 choose 2, 3 factorial minus 5 choose 3, 2 factorial plus, okay, maybe I should copy this since I'm getting stuck while writing. So this will be the answer. 5 factorial minus 5 choose 1, 4 factorial plus 5 choose 2, 3 factorial minus 5 choose 3, 2 factorial, 5 choose 4, 1 factorial. So, and this will come out to like this will be 5 factorial. This will also be 5 factorial. So these two terms will cancel out. This will be something like 5 choose 2 is equals to 5 times 4 divided by 2, which is 10. So this will be something like a 60. 60 minus 20 will be 40. 45 minus 1. So answer will be 44. So 44 is the correct answer. So I have just underlined this. So yeah. So if this is clear, then maybe we can move on to the fifth question. So for fifth question, how should I explain the fifth question? I believe you guys must have. Yeah. So maybe I believe like for this question, I hope you guys have seen bit of lecture, so you know what a Catalan number is. So for this question, the concept of Catalan numbers will be used. So the question says, in how many ways can 10 points on a circle be joined to form 5 lines such that each line joining a pair of points in such a way that none of the lines cross each other? So basically we are given 10 points and we need to sort of pair up these points. So there'll be sort of 5 lines formed by pairing 5 pairs, by forming 5 pairs, so that none of the lines should cross each other. So we need to count this. So let me just present a picture for this question. Just So these will be the 10 points which will be in question. Like let's just say these are the 10 questions, and these are the 10 points which we have, 1, 2, 3 up to 10. And we sort of like, let's just say we have labeled these points in this clockwise direction, that we have this point 1, point 2, point 3 up to point 10. And now what I want is I want to uh, get the number of ways in which I can form lines so that none of the lines cross each other. And I need to form 5 lines. So let me just maybe let's just try to do this using sort of a recursion based argument, right? So for recursion based arguments, how do we proceed? So let's just say, so T of n, let's just say I define T of n uh, as the number of ways in which 2n points. So you will understand later why I have defined this 2n for this T of n, in which 2n points can be joined to form n lines. So so basically, in this question, like we have 10 points and we need to form 5 lines. So in general, I have defined T of n as we need to form n lines out of 2n points, so that no two lines cross each other. So note that for every point there can only be one line. Like this point 1, let's say we have these points from 1 to 10. So this 1 can be either joined with 2, it can join with 3, it can be joined with 4, up to it can be joined with this 10 here. So now to derive the value of Tn, maybe we can write some sort of recursive function. So let's just see here. So let's just say we take the point 1 here and try to form lines for this point 1 on different with different points. So suppose this point 1 was matched with point 2. Like a line was formed between point 1 and point 2. So let's just calculate Tn. Like I'm writing a recursive relation for Tn. So Tn can be written as, so this point 1 can be sort of paired up with point 2, with point 3, point 4, up to, let's say here n is 10. So it can be paired up to with point 10. So let's just take the case first of all where it is paired up with point 2. So now the remaining, so if 1 and 2 are paired, then the remaining n minus 2 points can be paired in any way possible, because they won't intersect with this line 1 and 2. So we just need to take care that these don't intersect with each other, but we can be easily sure that they won't intersect the point, the line between 1 and 2, because this line is above all of these points. So this is sort of clear. So if we have formed one line, then we have one line less to form, right? So T of n will be equals to T of n minus 1 if like point 1 is paired up with point 2. Similarly, let's say point 1 is instead paired up with point 3. Let's say point 1 is paired up with point 3 instead. In that case, basically, what will happen is what I'm trying to claim is 1 cannot be paired up with point 3. Because if 1 is paired up with point 3, then since 2, then 2 will need to be paired with some point from 4 to 10. So it will sort of intersect with this line 1 and 3. So what I'm trying to claim here is that between 1 and 3, there are odd number of points. So at least one point will have to sort of cross the line between 1 and 3. So that's why 1 cannot be joined with 3. If it joins, then there will be 0 number of ways to form such lines. Similarly, if 1 is joined with 4 here, if 1 is joined with 4, then note that we have split the circle into two halves. One part has the points from 5 to 10. The other part has these 2 points of 2 and 3. So note that these 2 and 3 can, so these two parts are independent. So these 2 and 3 can be joined in T of 2 ways. And this sort of remaining 6 points basically. So maybe I should write it in form of t of 10 only. So this t of 10 or t of 5, since we need to form 5 lines. So if first line was between 1 and 2, then it will be this t of 4. And suppose instead this point 1 is paired up with point 4 here, instead of pairing up with point 2. If point 1 is paired up with point 4, at that point, the circle splits into two halves. One half has unpaired points as 6 unpaired points. The other half has 2 unpaired points. So we need to form 3 lines in one half and 1 line in other half. So this will be something like t of 1 for the half of 2 and 3. And since these two halves, upper and bottom halves, are independent, we can multiply their number of ways. So it will be something like t of 1 times t of 3. And similarly, let's say instead of pairing up 1 with 4, if we paired up 1 with 5, then we again have 0 ways, because these 2, 3, 4, there will be odd number of points. So one point will have to cross the line of 1 and 5, which will not be possible. So with 1 and 5, we'll get 0 ways. With 1 and 6, if we pair up 1 with 6, we'll have like 4 points on one side, 4 points on another, and these 4 points can be sort of paired up in any manner possible in t of 4 times t of 4 ways. So it will be something like t of 4 times t of 4 when 1 is paired up with 6. And similarly, when 1 is paired up with 8, then we'll again have this sort of relation of t of 3 times t of 1. And then we'll again have something like a t of 1. When 1 is paired up with 10, the remaining points will be paired up in like t of 4 ways. Or let's just say t of 1. Yeah, something like this. And maybe if we just define t0 to be 1, we can sort of write this t of 4 as something like a t of 0 times t of 4. So, so I hope this sort of recursion is clear to you guys, like how do we arrive at this recursion? So we just take the number 1 and try out different cases if the point 1. So if point was paired up with 2, if it was paired up with 4, it was paired up with 6, and so on. And we obtain this sort of recursion. Right? So for a general n, what will this recursion look like? So for a general n, like this was only like I illustrated only 10 points, so I derived the recursion for t of 5. For a general n, this recursion will look something like a summation of, maybe I should insert a symbol or something. Oh, yeah. So this will be something like summation of t of k times t of n minus k minus 1. So it will be something like this, where k goes from 0 to n minus 1. I hope you can see how is this the case. So this was something like t of 0 times t of 4. So this will be like if k was 0, then this will putting n equal to 5 here. So k will sum from, let's say k was 0, then it will be t of 0 times t of 4. Then if k was 1, then it will be t of 1 times t of 3. If k was 2, then it will be t of, this will be t of 2, sorry. T of 2 times t of 2. Then if k was 3, then it will be t of 3 times t of 1. If k was 4, it will be t of 4 times t of 0. So yeah. So this is the sort of summation, and this is sort of a recursive relation for general n. You can see the bounds for k yourself, that it will be from 0 to n minus 1. It doesn't matter much. So this will be a recursive relation for general n for this problem. In how many ways? Suppose if it was not 10 points but n points. So how many ways can n points on a circle be joined? So this will be the number of ways in which n points can be joined. So and note that if you guys have seen the if you guys have seen the lectures, then this recursive relation is called a special number. Like this recursive relation belongs to a special number. And do you know what that number is? So okay, so you don't know. So this is called Catalan number. And you should see this has been covered quite extensively in the lectures. This recursion is the recursion for the Catalan number. And um, this has been derived in the lecture, so I'll not derive it, but its solution, the solution to this recursion, the solution to the above recursion discussed in the lectures is nothing but this formula, like 2ncn and whole divided by n plus 1. Or there's a better way to write it, 2ncn minus, we should write it this way, 2ncn plus 1. So this is what we call the nth Catalan number. This Tn, which follows this sort of recursive relation where t of 0 is 1, is called the nth Catalan number, and it is equal to 2n choose n minus 2n choose n plus 1. So I really recommend that you watch the lectures based on these, which were so this concept of Catalan number and this recursion was covered in this week's lectures. So this was something which was not trivial and would require you to see the lectures to get a better understanding for this. Otherwise, you won't get a proper understanding for this. That's why I would recommend you to watch this lecture. So the answer here is the answer is nothing but nth Catalan number for us, and uh, yeah. So the answer for us is basically t of n equals to this 2n choose n minus 2n choose n plus 1. So here we need to find out in how many ways can 10 points on a circle be joined. So to find out how 10 points can be joined, here we took t of n as number of ways in which 2n points can be joined. So basically if we have 2n points, like we are in the, so if we have 2n points, then the answer is essentially 2n choose n minus 2n choose n plus 1. This is the answer when we have 2n points. And in the question, we are given 10 points. So we'll just put in n equals to 5. So I hope this is clear, like how I will put n equals to 5. Putting n equals to 5, we get t of 5 is equals to, like it will be something like 10 choose 5 minus 10 choose 6. If we choose n equals 5, will be something like n choose 5, 10 choose 5 minus 10 choose 6. And this will come out to be how much will it come out to be? It will come out to be 109876 divided by 106 will be something like a 2. So 987 divided by 12. 987 divided by 12, and it will be something like 927 divided by 3. It will be 327. So it will be something like a 42. So this will be the answer. So you can verify it yourself also. This 10 to 5 minus 10 to 6 will equal to 42. I just did this orally. So yeah. So 42 is the correct answer. So I hope you understand why we put n equals to 5, because we actually took two endpoints as t. In Tn, we actually took two endpoints. Like if we need to form n lines, that was what we meant by t of n. And here we need to form 5 lines. So 5 lines will be formed when we put n equals 5. So this is what we get as 42. So note that even though we got this recursion, getting from this recursion to recursion part is getting to the recursion part was not so difficult. Like we did this by straightforward thinking. But solving this recursion to actually get t of n equals to 2n choose n minus 2n choose n plus 1, this is not trivial at all. This is something for which you will need to see the lectures. Uh, this requires some more arguments, and yeah. So I would definitely recommend checking out the lectures on Catalan numbers for this. So now maybe we can move on to the next question then. Sixth question. Oh, okay. So sixth question was actually a question which I do not want to discuss that. I did not want to discuss it that much in the class. Or should I discuss? Let me think. Okay, I guess I can discuss the high level of this. So yeah. So even though sixth question is a very straight, like it's just a very calculation based question, but a very straightforward question. Like this concept has been covered in the lectures, like how to solve non-homogeneous recursion. This belongs to that part only. Like so, the question is basically which of the following is a solution to the recurrence relation given as this: a of n equals to 4an minus 1 minus 4an minus 2 plus n plus 1 times raised to 2 raised to the power n. So we need to solve this recurrence relation. And for this, so for solving any recurrence relation of this form, so this is a non-homogeneous recurrence relation because there is a term which is not of the form ck a of n minus k, right? This n plus 1 2 raised to the power n form. Because of this, this is not a recurrence, homogeneous recurrence relation. So this comes under solving the non-homogeneous recurrence relations. So how do we do this? So just to remind you, like, how do we do this? This has been discussed in the lectures, but just to remind you, so what do we do here? We break up our recurrence into two parts. So we first focus on the homogeneous part of the recurrence, and then on this later term. So we sort of find a homogeneous solution and a particular solution, and then proceed. So maybe I'll just write it down now. To solve the so first of all, this is a non-homogeneous recurrence. So to solve this, this is probably wrong. This is what to solve this. We first find the homogeneous solution and then guess a particular solution satisfying the recurrence. So for this, I'll also recommend checking out the lectures because there are a lot of cases in, like, if the recurrence relation is of this form, then how do we proceed? If recurrence relation is some other form, then how do we proceed and stuff like that. So I'll only be covering this recurrence relation, but there are some other forms of recurrence relations also. So for that, you will need to check out the lectures where we solve the non-homogeneous reconciliations. So yeah. So this is one of the cases, but there are many other cases also. And so you'll need to check out the lectures to understand how do we solve, how do we proceed in general for all possible cases. Right. So so we first find the homogeneous solution and then guess a particular solution satisfying the recurrence. So finding the homogeneous solution is easy, and we'll just do that first. Finding the homogeneous solution. So what's the homogeneous solution? What does homogeneous solution mean? So homogeneous solution is nothing but just finding a solution to the homogeneous part. So homogeneous part is the part where we exclude the extra term, which does not contain a ck of ck into a times n minus k term. So this term n plus 1 2 raised to power n of is not a type is not uh, like these terms, right? These terms have the form of a coefficient, a constant coefficient times some a of n minus k, a of n minus 1, a of n minus 2, and so on. So, so what we'll sort of do is, so if we first find out the homogeneous solution. So the homogeneous equation will be homogeneous part is nothing but this one where a of n is equals to 4 times a of n minus 1 minus 4 times a of n minus 2. So this is the homogeneous part of the recurrence. So to solve this, we know how to solve this. To solve this, replace an. Okay, replace an by x square. We have covered this in last session also. So this is something which is straightforward. So to solve this sort of recurrences, we just replace an by x square, an minus 1 by x, and an minus 2 by 1. An minus 1 by x and a of n minus 2 by 1. So we get the equation x squared is equals to 4x minus 4. And from this, what we get is x. So, uh, so from this, what we get is x minus 2 whole square is equals to 2, is equals to 0. So you can easily see that this implies this. So what this means is that x equals to 2 is a repeated root. So basically the only solution to this reconciliation is x equals to 2. So it's a repeated root, that 2 is a root 2 times. So in this step, this was covered in like last week's lectures. Uh, like if we get a repeated root, if we don't get repeated root, like if we had got two different roots alpha and beta, then our solution would have been of the form c1 alpha to the power n plus c2 beta to the power n. But if we have repeated roots, then the solution is of the form, since we have repeated roots, the solution is of the form c1 2 raised to the power n. So like I said, c1 alpha to the power n plus c2 beta to the power n is the form if alpha is not equal to beta. But here alpha is equal to beta since both roots are equal to 2. So here the solution is of the form c1 2 to the power n plus c2 times n times 2 to the power n. So this has also been covered in the lectures. You should see the lectures to know why is this the case. So yeah. So anytime we have repeated roots, the solution is of the form c1 2 raised to the power n plus c2 times n times 2 raised to the power n. If the root was alpha, then we have alpha to the power n and then n times alpha to the power n. So this is the homogeneous part of the solution. So homogeneous part of the solution is this. And now we sort of need to guess the particular solution. So finding the particular solution. So while finding particular solution, so there was also a set of rules which were given in the lecture. So if this fn is, so fn is of the form n plus 1 times 2 to the power n, right? So the extra term which was given to us in this recursion is this term n plus 1 2 raised to the power n. So this fn is nothing but n plus 1 uh, times 2 raised to the power n. So for this, uh, you can see the lectures for this sort of situation. The particular solution is of the form uh, n square times. So note that this 2 raised to the power n. So here in Fn also we have this 2 raised to the power n term. And this homogeneous solution also we had this 2 raised to the power n term. So if the roots of the homogeneous part and this 2 raised to the power and this term coincide, then the particular solution is of this form, like n square times. So these rules can be checked out in from lectures only. Like this is not something which I'm doing by some reasoning or logic. Let's say these are some rules which have been covered in the lectures and I'm just applying them. So this is, so particular solution is of the form n square times an plus b. So basically the degree of this part is essentially the degree of this term here. So this is the degree 1 polynomial. So there will be a degree 1 polynomial here, an plus b, and then we'll multiply this 2 raised to power n. So this will be the particular solutions form. So this is something which I'm not claiming that I know how do we get to this. This is something uh, which can be derived from the lectures. And now plugging in the particular solution. Particular solution into the recursion. So if we plug this particular solution into this recursion, we'll get values of a and b by comparing coefficients of n and the constant coefficient. So maybe I should not cover all of the calculations and stuff, because like even if the main issue I have is even if I cover all these calculations, so if this sort of thing changes to some, if this fn changes to something else and the recursive relation changes, then some other rule must be applied. And all these rules, so you should sort of know these rules beforehand. Uh, and these rules have been covered in the lecture, so you must see the lecture beforehand. And if you know the rules, then it's straightforward. Then I don't need to discuss this anyways. So basically, just like I'm just discussing the high level solution on a high level now. So first of all, we solve the homogeneous solution and we obtain the solution is of this form. Then we find the particular solution using the rules, and we guess the particular solution of this form. And by plugging the particular solution into the recursion, we'll get the values of a and b. So we'll get here what are these constants a and b. And after this, we still need to determine the value of these constants C1 and C2. Then in the end, obtain the values of C1 and C2 by using the fact that A1 is 19 by 3 and A2 is 100 by 3. So using these two values, we'll get the values of C1 and C2 later. So I'll just leave you with this question, and I'll say that complete the solution yourself. So I've explained the high level idea, and then you should complete the solution yourself. I'll just leave you with the answer. So correct answer for this is, so this was the question. So correct answer was this option C. So after solving all of this and doing all of this, all these steps, you will obtain that an is of this form, like an is equals to n cubed by 6 plus n square plus n plus 1 times 2 raised to the power n. So answer C, option C is the correct answer. So yeah, I guess I should leave the sixth question at this, like, because I don't want to do these calculations and stuff. Because even if I do, if question changes slightly, the idea also changes, and so it's useless to discuss. So you must check out the lectures for this week to get an idea of how to approach these questions. So yeah. So uh so seventh question is an interesting one. So seventh question says, uh, if a man climbs either one or two steps at a time, the total number of ways in which he can climb up a staircase of 2n steps, starting from the bottom is. So what I'm claiming is we have sort of discussed this sort of question before also. Uh, in I guess previous session or some like previous to previous session. So question is asking a man can climb either one or two steps at a time, either one step or two steps at a time. So the total number of ways in which he can climb up a staircase of 2n steps. And the options are given in terms of these combinations. So like he can either take one step at a time or two steps at a time. So if the staircase has 2n steps, then in how many ways can he climb? So how do we approach this question? So first of all, what I'm trying to claim is one way to count this, like if a man climbs either one or two number of ways in which he can climb up a staircase of 2n steps. So one way to count this is using recursion. One way to count this is using recursion. Like let's say T of n is the number of ways to climb a staircase of n steps. Like we are given 2n steps, but we'll just derive the recursion for n steps, and we can plug n as 2n. And in this case, what can we say? I remember that we had discussed deriving a recursive relation for this in one of the sessions. So let's just say, so we need to find the total number of ways in which the man can climb, right? So to find this T of n value, what we can say is the first step the man takes will either be one step or two steps. Only since the man has only two choices, taking one step or two steps. So if he chooses the one step, then there are only n minus one staircases remaining to be covered, right? So if he chooses taking one step, then there are only n minus one cases, n minus one more staircases to be covered. But if he chooses two steps, then there are only n minus two cases to be n minus two steps to be covered, and there is no other choice. So T of n is actually equal to T of n minus 1 plus T of n minus 2. So this is nothing but so we know how to solve this recurrence first of all. And another thing is this recurrence is special and it is called like this is nothing but the Fibonacci sequence, right? Fibonacci sequence is a sequence which is of this form that A of n is A of n minus 1 but plus A of n minus 2. So one way to count this is using recursion, like using Fibonacci sequence and all. We know that we can count the 2n steps one. But the options are not in form of recursion. They are in form of actual values like summation of some n choose r terms. So what I'm claiming is that we can count it this way also. So like basically a high level idea is a high level rule generally is like Same thing can be counted in multiple number of ways, right? There is no fixed way to count something. One can come up with some clever way. Other one is other one can count using some other complex ways and so on. So this was one way. Recursion was one way to count the number of ways. Another way is maybe dividing this into more cases. Like let's just say so man has two types of choices, right? That the man can take one step at a time, or the man can take two steps at a time. So let's just say by the time the man reaches the two n steps, the man has took exactly r of two steps, or maybe only like r of r1 steps. Like let's just say another way of counting. Maybe this will be the last question, and I won't discuss the eighth question since it's again related to Catalan number. Maybe I will, for eighth question, I'll just write it down. Write yourself. Int is use Catalan numbers. So yeah, for eighth question, I'll again say write yourself. Let's just make this seventh question as the last question for the day. So another way, so we need to count and how many ways can the man go to two in steps by using one step or two step at a time. So for this, one way is to count using Fibonacci sequence. Another way of counting is by taking cases on the number of one steps taken. So one steps, let's just divide like if I'm like one steps is basically when the man chooses to take one step instead of two steps at a time. So what I can claim is if the man takes, so by the end of the man's journey, by the time the man reaches the 2nth case, a man could have took like r number of one steps. If the man takes r number of one steps, one steps. So what this means is that the man had to climb two n steps. The man had taken like r number of one steps. So the man must have took like let's say so r steps were covered using one steps. So the remaining 2n minus r steps. What I'm trying to claim here is the remaining 2n minus r steps must have been covered using these two steps operation. Maybe I should present this a bit better. Okay. So let's just instead of these one step, let's just take two steps. Yeah. So man can take one step at a time or two steps at a time, right? So we are counting on by taking the cases on the number of two steps which are taken by the man, like the number of times the man takes two steps at a time. So if the man takes like let's say r number of two steps, like if the man takes r number of two steps, what it means is that man covers two r steps in this manner. So two r steps were covered in this manner, like by these two steps. So remaining n minus r remaining 2n minus 2r steps. So there were 2n steps in total. 2r steps were covered in two-step manner. So remaining 2n minus 2r steps are covered in one-step manner. One step are covered by one steps. So I hope this sort of statement is clear to everyone. Like if the man takes r number of two steps, so the man has taken two steps r times. let's say, or maybe yeah, if the man takes 2 steps r times, like r times is a better way of representing. So man has covered like basically 2 r steps in this manner by taking 2 steps r times. So remaining steps would be only 2 and minus 2r, because the man has taken 2 r steps by this manner. So remaining 2 and minus 2 r steps would be covered by these 1 step manner, right? So now basically what we have is we have 2 and minus 2 r 1 steps and r of these 2 steps, right? We had 2 and minus 2 r 1 steps and r of these 2 steps. And now these can be like permuted together in any way, right? We just know that there will be r 2 steps and 2 and minus 2 r 1 steps, but these can be permuted in any way. Like the man can first take a 1 step, then can take a 2 step, then can take a 1 step again, and so on. But we know that total number of 2 steps will be bounded by r, total number of 1 steps will be bounded by 2 and minus 2r. So total number of ways of permuting these 1 steps and 2 steps together. So basically, what I mean to say is we have objects of 2 types. One is of type 1 steps. We have 2 and minus 2 are such objects. And we have R objects of this 2 steps type. And we need to sort of permute these. So if we have like 8 n1 types of one object and n2 type of another object, then the total number of ways to permute these objects is just n1 plus n2, choose n1. So what I'm trying to claim here is this will be nothing but 2n minus 2r plus r, choose r. 2n minus 2r plus r, choose r. And why is this the case? If we have, uh, why is this the case? Like I'll just put it in parentheses. If we have n1 objects of one type and n2 objects of another, total number of ways of permuting them is equals to nothing but n1 plus n2, choose n1. And I believe this sort of formula, how does this formula come about, is sort of easy, because the total number of ways, if they were not distinct, is just n1 plus n2 whole factorial. But since n1 are of one type, we divide by n1 factorial, n2 are of another type, so we divide by n2 factorial. So it would be n1 plus n2 factorial divided by n1 factorial n2 factorial, which is nothing but n1 plus n2, choose n1. I hope it's clear. So basically total number of ways of permuting these 1 steps and 2 steps is equals to 2 and minus 2r plus r, choose r, which is nothing but equal to, like 2 and minus r, choose r. This minus 2r plus r becomes like 2 and minus r, choose r. So this will be the answer if we take 2 steps r times. But we have choice over r also, right? The man can choose that I want that r can vary from 0, like man can choose 2 steps 0 times, man can choose 2 steps 1 time, 2 time, up to n times. Man can only choose the 2 steps up to n times, because after, like man can't choose 2 steps n plus 1 times because there are only 2n steps available. So since there are only 2n steps available, if a man chooses like n plus 1 times the 2 steps, then man would go to like 2 times n plus 1 step, which is not possible. So that's why since R varies from 0 to n, hence the total, hence the total number of ways is equal to, let's say I'll just copy the sum sign. Is just equal to summation of this 2n minus r choose r for r from 0 to n. So this will be my final answer. And this is basically, I guess this option A is the correct answer, right? Option A has this 2n minus r, choose r, and r is going from 0 to n. In option B is going from 0 to n, which is incorrect. Option A, r goes from 0 to n. So option A is correct. Option A is correct. Okay. So yeah, I guess that's it for the day. This was the last question which I want to cover. Eighth question was something which I had in my mind, but I guess uh, it's just a straightforward application of Catalan numbers. So if you see what are Catalan numbers, you can just solve this question directly. So I won't be discussing this, but I'll leave it in the practice sheet just so that you can try it yourself. Okay, so we have like we have short over time, like we are over by 2-3 minutes, but still like if you have any doubts in this seventh question, or if you have any other doubt left, maybe I can try to answer those in like for 2-3 more minutes or like 5 more minutes. So Priya, do you have any is the seventh question which I discussed this question clear? Like how did we obtain this 2n minus r choose r? Um, so if you have any doubt in this solution, maybe I can try to answer your doubt. Okay, please typing something. Okay, sure. Uh, yeah, maybe listening to the lectures. Yeah, after listening to the lecture, you'll get a better idea. Although I feel like the seventh question does not require use of much use of the lectures. Like seventh question is sort of independent of the lectures. Like they lectures are more based on principle of inclusion, exclusion, and stuff. Seventh question was more related to counting only. But yeah, you're saying you got the idea of this, then I guess it's fine. Maybe if you like, if you have a high level idea, then maybe you can just go through the video again or just read the solution again and you will be able to understand. So yeah. And if you're not able to understand, like you can ask me in the next session also. Okay, so sure. So uh, so I'll assume that if you don't have any other doubt, then maybe I can stop recording and we can close the session. So yeah. Yeah. So I guess no one has any other doubt. So yeah, thanks everyone for joining. So I hope I'll see you guys in the next session also. So yeah, for now I'll maybe we'll close this session. So bye bye.